let me start with the content. So the idea here is to give application view of electric vehicle for the electric drive design. So the application here is traction or the electric vehicle. So how the conventional machine design or conventional inverter that is electric drive, how it will change, how it affects. So these are the generic contents covering various aspects like sizing, thermal consideration, harmonics, some trends in the industry, and vibration, some mechanical issues. So the content by and large cover various aspects, and we will go through the first aspect, that is the we call this is a requirement. So the first requirement for any say vehicle is the torque speed curve. So our existing IC engine and the transmission, that is the gear ratio that we have, that gives us a typical performance. So the on your left hand side you can see the engine uh, curve, and then with gear you can see the torque speed curve with the gears. So the thing is electric drive is very much close to this kind of a requirement, and the that is one of the reason that it goes very well naturally with the requirement for the traction applications. So we get the very good torque at the beginning, and then the torque drops, but we get the power. So this is ideal torque speed curve, but the nature or the behavior that we expect for the machine is almost what the IC and gear can do. So this is where we say that okay, this may be a good alternative for the IC engine. The another aspect is efficiency. So the traction requires different drive cycles. So we have say very say city drive or highway drive, aggressive drive, urban drive, rural drive. So these different cycles demands different torque and speed curves, and their operation, the frequency or the we call this as a heat map, where mostly the vehicle will be operating in those different cycles are plotted here, and that becomes input for designing the electric drive. So you can see the efficiency requirement varies, and the operating point, these dots that if you see here, those are the operating points, will be different for on this torque speed curve. So if I plot those, consider some 3 to 4 drive cycles like this, and plot those couple of cycles here, so you can see the operation of this particular cycle, that is in red in color, is more across the torque speed curve, but you can see the blue one is concentrated more on the high torque zone, low speed. So this actually gives us a lot of insight to design electric drive, where we should be designing, in which area, where we should focus, which part of our operation should give most efficient part, because it's very difficult to give the maximum efficiency at all torque speed points. So we have to see where the most of the time machine or traction demands operation of machine, and there we can try to optimize it. So this is very good requirement that traction specify to any electric drive design engineer. The another requirement coming from the say Department of Energy. This is a regulatory, or this is the one of the bodies that they uh, they drive the development and research. So you can see we are almost in 2020 here. So these are the years. This is a drive system, complete electric drive. This is a power electronics, mainly the inverter, and this is the motor. And these are the key driving elements at a very high level, that is dollar per kilowatt of energy. So these are the densities and volumetric density, kilowatt per liter, and efficiency. So the DOE, Department of Energy, see that this target, how we move towards this target. And now already we are in 2020, and we are very much close to these numbers already we have surpassed in few areas. So in case of inverters, we are well above this number. And the next targets are being will be set up soon by the DOE. But in terms of cost, it's still not we are there. We are still struggling to get to these numbers, close to these numbers. So this is very good, say I can reference chart where you can see where your design stands and where you want to move forward. And there are some research areas mentioned here, which you can go through later on. So these are the some of the key areas that they have mentioned here. The cost wise, so the another element is where is the most of the cost coming from. So the magnets in a permanent magnet machine is coming from the magnets, which is 53% close to. And this is the, I mean, this is the target that 2020 wants to go to the 4.7 dollar per kilowatt. And this is the sort of a, say existing state, which is a year before, but this is almost pretty same now also. And this is for the inverter. And put together power electronics, the inverter, converter, transmission, you can see we still have this a lot of cost coming from the inverter side. And the transmission is also playing a big role, whereas the machine is something close to 20%. And these days this transmission cost is also going down. So just to put some reference, this is from Delphi, one of the presentations that Delphi put together for Department of Energy. Is this is what they have achieved so far in terms of densities and in terms of cost. So they are claiming that their cost is much close to what DOE has specified. So this is their claim, and we have to check this in reality. But this indicates just, I mean, this is just to indicate that we are moving in the right direction. Whole industry is moving towards that. The other consideration for electric drive is the what kind of voltage and current available from the battery. So that is a big constraint. We have to consider that what kind of power and energy is available, because battery is a balance or trade-off between energy and power. So we have to consider what kind of a peak current, what kind of a continuous current we can draw from the battery, and what we can deliver with that from the machine or from the inverter. The other constraint is also coming from the switching strategy that we have. So we may have different switching strategies that introduce harmonics, or that reduces harmonics. And those switching strategies impact us. So we should be very much having know-how of what inverter team is doing, what inverter people are trying to do, what kind of harmonics they are introducing, what kind of a efficiencies they are talking about. So the available from battery and the switching strategy is what majority of the time forms the design space for the electric drive. So the sizing part. So let's say we know the constraints, we know the environment, where we know the application well now. Coming to the sizing or scaling part, we know that this torque is proportional to the d square L. So this is the by and large what we see well accepted analytical form. Uh, the most say attractive thing is the length of the machine, and that is where most of the say electric machine manufacturer plays with it and gives different powers and different torque. That is a one key element. But the thing is, when we increase the length, essentially power may not be linearly increasing. So we have to look at the losses and the efficiency as we keep on increasing the length. And then we once we hit that limit, we have to look at the what kind of current and voltages that we have from the battery. So more voltage is more power, more current is more torque. So something we have to see where we have to strike balance up to what limit we can give torque, what kind of a length and diameters we can play. So the diameter also plays key role. So as we keep on increasing diameter, we have more benefits, but that benefits comes with it because this is in square term, but that comes with a little bit of the money. So the tooling cost increases as we because our the stamping, the diameter, all the parameters increases new tooling, whereas the length increments needs less investment. So the cost versus design is where we have to trade off here. The key thing is we have to keep the design as far as possible modular or scalable. If I want today say 100 kilowatt, is it possible to get 150 kilowatt or 120 kilowatt by increasing some length or by doing some better cooling? So the modularity is a key in industry, where the same platform of machine or the lamination can be used for various vehicles. So that gives huge cost benefits to the OEM. The other side of it is the application. I mean, the other side of application is when it vehicle moves, there are different loads coming on the electric machine. So that also we have to meet, not just the drive cycles, but there are the elements like the climb uphill or start on hill. There are many other situations where we have to size the machine to address those requirements. So the requirements those form for typical conventional vehicle will also be applicable here. But from machine perspective, we have to see we have enough current, we have enough voltage, we can deliver it to the maximum speed required that vehicle has to attain, and the all the starting conditions, all the gradients that it has to go through. So those are depicted here in the chart. This is just a reference chart where we try to plot different conditions and make sure that our torque speed curve of machine satisfies the different requirements. There is a peak requirement, there is a continuous requirement. So both conditions we have to put here, and that is where you can see the electric machine torque speed curve is for peak as well as continuous in this chart. The another consideration is what kind of a machine we should select, whether it should be high torque or low torque, high power or low power. And you can see here it's two typical machines where the power of these two machines are same. Let us say that they are having the same power. And you can see which machine now we should select, whether they are having say 50 kilowatt, 50 kilowatt. But you see here the volume of P would be much lesser here in this case. So it is again the space availability, what kind of a requirement we have to meet. Those consideration will go when we select such kind of or design any kind of electric drive kind of. So you see here different machines are designed from various power, so 44 kilowatt. But this particular raid, say, performance, you can see it has low torque, but it sustains that torque for much higher speed, and then it starts dropping. Whereas this blue color is at low speed itself, it start dropping. That is a 44 kilowatt machine, and it's very high torque here. So which one to select? So there may be another criteria to select this is acceleration, because this is where we have to look into this, whether you need a sustained, more sustained torque for higher speeds. That will give us a very quick acceleration. So you can see the raid, the top raid is what the machine of 80 kilowatt that we were discussing currently, and something this 50 kilowatt or 44 kilowatt is much lower in this. So it may give very good instant torque, but it is not able to sustain it. So you see here the acceleration versus speed is something we should always be looking at. So the selection of machine or design of machine, uh, say, govern these kind of parameters from the vehicle side. The another thing is the transmission, which where this machine is connected. So if we have a two-speed transmission, then you can see here the green part of this torque speed curve is catered. Whereas if we have a single gear, a single speed transmission, maybe we can do this the whatever the orange part, but not the green part. And also at high speed, you can see the second speed transmission is giving me a much higher, much higher benefit to increase the vehicle speed. So the gearing and machine goes hand in hand. So what kind of a ratios we should have there? So typically say 9, 10, these are the typical ratios that we have for the first gear. And second gear, we may so there may be multiple gears, so there are a lot of discussions going on multiple transmission, multiple gear transmission systems, which gives much better, lower the size of the machine and gives better performance. But on the contrary, we have some challenges with transmission as well when it is a multiple transmission system. So this is another trade-off that we have to study when we design machine. Uh, then the another element to consider for machine design is what kind of a VDC or DC bus voltage we have and how we are getting that. Many architectures, high voltage architectures, got a boost circuit, that is a bidirectional DC-DC boost converter. That may not be necessarily each OEM has or got. So, like for example, Price introduced this. So that drastically reduces the battery terminal voltage, that to say 200 volt, and then we can still have VDC at 500 volt. That voltage is going to impact us on electric drive when we design electric drive, because that 500 volt, that means I can have much higher back EMF, so I can run at very high speed, and I can have different characterization or different torque speed characteristics of electric machine. So this is another important consideration, what kind of architecture we have in place for electric machine design. So coming to the electric machine as such now, so we know our environment now very much well. Now we are conversant with what parameters are driving the electric machine design or say inverter design. So mostly we will see induction and interior permanent magnet machines. These are predominantly, I won't say uh, those are the only machines, but those are the dominated machines that is being used because of their robustness. Maybe we have put a lot of research in that area. But there is another consideration going on, because you remember that magnet cost is almost close to 40%, 45% of total machine cost. So there is a wound synchronous machine that is coming up, which is shaping up. Or there are other different machine topologies where less amount of permanent magnet is used, or ferrite is used. So less rare earth free permanent magnet machines, or electric machines are being researched. And different winding topologies are also being studied along with that. We can see here, these are the different, even the SRM machine is also in brace, and we can see different windings that here at the bottom also drives those design. The hub motor, which is I think is also in consideration, and that is called outer rotor permanent magnet machines. They are still, we don't as an industry, we are still not considering that as a mature solution. We see a lot of development happening, a lot of claims are being made, and a lot of vehicles are being developed there, but there is no mass deployment as of now with these machines so far, in the at least in the four-wheeler and the bigger say commercial vehicles.